Okay. Okay.
Sunny day.
Can I just tell you how much I've already clipped off my list?
See, look how
Rhonda, R-O-N-D-A, and then the last name's McCowan, capital N, small c, capital K-O-W-N.
yellow. Yeah. So I'm more actually. Yeah.
2, 3, 4, 5, 6, 7, 8, 9. I'm gonna say 10 to 12, but it's 12 invited, but I doubt we have that many show.
You just had to make sure that they was available 21.
At 6 p.m. 6 to
So, which I'm pretty sure you are. You'd have to
come early and move the tables. I need to.
You're breathing so loud, Spaghetti. Okay. All right, everybody. Give me a minute. I got caught up updating some stuff. If you guys didn't see, I just posted on the announcement like my little study layout sheet for each chapter. I make one for every chapter, even though I'm not necessarily sharing them with you all, and I definitely shared 11 and I have 12, but I just posted 15 and 16. Yes, I'll probably also post 12 and have all of them posted for you guys at some point. I'm not going to guarantee anything on 17 or 18. Maybe 17. I don't know for sure about 18. 18 is a pretty easy chapter, I'm not going to lie. So we will be looking at that. But those are available on the announcement page as well as on the discussion page where all this other stuff is posted. Okay. Anyways, let me go ahead and share my stuff and we'll get started. Come on, come on. There we go. Okay, PowerPoint. Okay, so obviously week 10 is going to have to do with our chapters 15 and 16. I don't know why I have. Okay, whatever. Erase that. I wish there was an easier way to select the eraser. Okay. Keep hearing stuff outside, you guys, that I'm like, is it the wind? Is it, I don't know what's going on out there. I feel like my whole house is falling apart. Okay, let me be sure to, because I don't have my sound turned up on this. Yeah, I do. Okay, cool. In case you guys were talking. All right, so 15 and 16, we know this is innate immunity, and this is going to be also our adaptive immunity. And then, so let's get into it. So our innate immune topics, of course, the things that we learn about are going to be our first line of defense stuff. That's everything that's going on like on the body and in the body that just exists naturally, that is also helping keep out our pathogens like your skin, the hairs in your nose, the cilia in your lungs, moving the mucus out, your normal biome. And then we learned about two terms about the lysozyme and the keratin. These are like just terms, again, flashcard terms. If you don't know what these are, you may have heard of keratin, but you need to know that it is our waterproofing protein. that seals basically our skin with, you know, its existence, the fact that it's creating that barrier that prevents microbes from literally getting into the tissues underneath the skin. And we have lysozyme, that's an enzyme that specifically breaks down peptidoglycan. It's found in your tears and in your saliva. It's a very useful way of keeping bacteria under control. But most of the chapter talks about that second line of defense and introduces concepts for the third line. And of course, the chapter 16 is mostly third line stuff, the details behind how it truly works. But in chapter 15, we get into the basics that all lymphocytes come from the bone marrow. T cells continue maturation in the thymus. A lot of our cells will set up, station in our lymph nodes and our spleens and other lymphoid, tissues, associated lymphatic tissues. The ALTs, like the skin associated, the gut associated, and various mucosa associated lymphoid tissues. So salt, malt, and galt, those guys. They have similar function to what lymph nodes do. So they're going to involve housing a whole bunch of lymphocytes, as well as helping filter out lymph on its way back to rejoin the circulatory system. Oh my God, Spaghetti. No, you're so cute. I know you're a little noodle. I know it. I know. Okay. I'm sure you guys can hear him breathing. It was a little tiny dog breath breathing. Alrighty. I know. So, jeez. Okay, so just sit down. Plasma and versus serum. Serum is going to be our, when we have, sorry, I have to go somewhere else. These dogs are ridiculous. They'll be quiet for so long, you guys, and then all of a sudden they're like, oh, mommy's talking. We need to go attack her. Anyway, so the plasma is whenever you have blood that has essentially been treated in a way so that it doesn't clot. And the liquid that you would get when you separate it out after doing that is plasma. If you allow blood to clot and then separate out liquid, that's going to be your serum. Stop it, you guys. Okay. Lymph itself is essentially the liquid portion of blood. So you could look at it as being essentially a representative of serum and not so much plasma. Even though it's not clotted, I understand, but it still contains everything that serum would have and the functionality of what serum would have, but in like its active, natural, unclotted state. And so it has that as well as things that you would find in plasma. So because it's the living version of that, that liquid portion can itself migrate out with any of the cells that could be involved in an immune response. Any of your leukocytes, which are your white blood cells, migrate out into the tissues. The red blood cells do not go with it, but whatever liquid and cells and nutrients and other like clotting factors and healing factors might need to go into an injured area, all of that will migrate into that injured area based on signals that the injured tissue is sending out. And those chemical signals are called cytokines or chemokines. Those are interchangeable for our purposes. So chemokine or cytokine, think of kine as a signal and cyto being, of course, cell signal, chemo being just the fact that it's a chemical. So that's why I say they're interchangeable. And of course, the cyto part just says that it's coming from a cell. So anyway, so these signals are calling everybody in for the immune response, and the liquid comes with it. The cells can also migrate between the tissues using that mononuclear phagocyte system, the MPS. So that is just our like highway that allows for passage between tissues and cells and organs and all that stuff. So we can migrate between and help spread that immune response more effectively instead of always just relying on the capillaries to bring us to locations. We can now migrate outside of the bloodstream. So that's the MPS. That's this guy here. All right, we already said about the white blood cells. So you can divide up your leukocytes, your white blood cells. Of course, not them walking around, they're just laying there. Of course, you're going to divide up your white blood cells, your leukocytes, same thing. into two categories based on literally when you're working in hematology in a lab for a hospital. Hematology is looking at the blood cells and the blood cell types and the counts and your hemoglobin and all of that stuff. That's what the hematology people are doing. So they are going to do stains on your leukocytes, and the ones that show literally when you look at them, this is not anything beyond that, okay? When you look at them with the stain, if they look like they have little granule type structures in them, we call them granulocytes. If they don't, we call them agranulocytes. So A being without granules, So that's our two categories of our leukocytes, and those categories stick, and they in fact have to do a little bit with the functions of these guys. So our granulocytes include all of our fills. Those are the ones we focus on first. Our other granulocyte you just have to be aware of is the mast cell. Again, they work kind of similarly to the fills, but they're not as important in the phagocytic response to things, okay? So they're mostly going to be like chemokine releasers or cytokine releasers to help call in the guys that are going to do the big phagocytic type of like eating up of pathogens and stuff like that. All right. Cool. Now, what do I want to say about this? The agranulocytes, these are going to be the ones, again, without the granules. This includes monocytes and lymphocytes. So that's our categories. Within the lymphocyte category, we know that we have the B lymphocytes and the T lymphocytes, which we talk about in chapter 16 more. Whereas in the monocyte category, a monocyte is a type of cell on its own that circulates in your bloodstream. It is a phagocytic cell. So it has the ability to eat up any of these pathogens. And it has a big old nucleus, which is why it's called a monocyte. It's a big old single nucleus, whereas these fills get a little bit iffy with how they organize their nucleus, okay? They look like they've got lobes on their it's just weird stuff. But our monocytes have nice, big old, fat, recognizable nucleus, and they will go into your tissues when they're called in there, and they will differentiate when they get in there. So once they're called out of the bloodstream and they move into the tissues, they will essentially be assigned to those tissues. And then they become macrophages or dendritic cells, depending on what tissues they go to, and likely may stay assigned to those tissues for the remainder of their life. And they used to be monocytes, but now they're macrophages and dendritic cells. So those are kind of the same thing. It's just different ways of looking at those same things. So I'm just realizing like how off center my couch is. Standing in the kitchen looking at it. I guess I never really thought about it before. Anyway, so the right. So as far as phagocytes go, we have a few guys that are in our repertoire of phagocytes. These are going to be mainly your neutrophils, and then your macrophages, your any of the monocyte derivatives. Those guys are going to count as your phagocytes. And then mast cells can be phagocytes. That's just not their primary role. They're mostly going to be signaling molecules. Like I said, they're going to be like the scouts. It's like if you have scouts out there in your tissues that are always looking out for invaders, always looking out for the bad guys, and then you gave them a pistol. That's sort of like what you've done. But they have a working radio to call in, everybody else. So it's kind of what the monocyte or what the I can't talk right now. Mast cells are going to be like. So not super effective. That's not their main role, right? That's not their main role as cells in the immune system. They're mostly there for signaling and mediating our response in the immune system. Yes, I am actually literally moving my couch while I'm talking to you guys. Okay. Cool. So, but yeah, we want to think more about the monocytes, macrophages, and dendritic cells coming from those monocytes. So of course, they're all going to count as a phagocyte. and then the neutrophils. Those are our biggies for our phagocytes. All of these innate immune responses are going to be triggered and guided by recognizing PAMPs, those pathogen-associated molecular patterns. Like we said, anything that is a general marker of bad guy. If you have peptidoglycan, you don't belong here. If you have LPS or endotoxin, you don't belong here. And that sort of stuff is what we're talking about with a PAMP. So it's a repeated pattern that's found on the surface of, generally speaking, like bacteria. And it's just weird, when I stand in from this angle, it looks like it's one way. And then when I stand at this other angle. So anyways, it's just gonna bother the living heck out of me. It has something to do with the furniture, I think, around it. So yeah, so those guys, those repeated patterns that can be associated with any pathogens. So then things that are going to be like, obviously going to be like the peptidoglycan and the LPS, but also the double-stranded RNA, which is a genome type that some viruses can have. And in our own cells, we never have double-stranded RNA. So that's why that can be a trigger for us as far as like the fact that it shouldn't belong there. So that's the idea with that. Okay, the PAMPs. Anything that you can see as definitely not self, essentially, we probably have some sort of PAMP associated with it. This is found on a lot of bad guys. They're all wearing freaking black, ski masks, black balaclavas. This is a problem. We need to get rid of these guys. That's essentially what that is. So that's the PAMPs. So that signals phagocytes to go around and eat up these guys. They do have receptors on the surface of their cells that are called like pattern recognition receptors, go figure. And those are very generically going to be interacting with those PAMPs. So again, not a specific response, a very generic, very general response. So we recognize a PAMP, we go up there, we see the peptidoglycan, and then now that signals for us to be like, oh, yep, you're wearing this balaclava, now I'm going to be eating you up. We go through phagocytosis, and the steps are, of course, we got called there via chemotaxis. So there was some sort of signal that called the neutrophil or the macrophage to that area where the injury or infection is happening. Other cells in the area were saying help, help, help. And they got called in from the bloodstream into these areas, or from nearby tissues into these areas. That's chemotaxis, responding to the chemical signals and moving towards those like you would towards a plate of cookies. Just like the bacteria do when we talked about how they will move with their flagella. It's the same exact thing. These guys don't move by flagella, though. They're moving via the bloodstream, and usually it's also going to be by that sort of amoeboid motion, using like the parts of the cell to kind of scoot along with things. Just so you know, you don't need to know that for the test, but that's how it works. Once we get to there and we've recognized a PAMP in the area we were called to, now we can ingest the guy that had the PAMP, the balaclava or ski mask that it was wearing. And then eat that guy up, put him in our phagosome, which is just the vesicle that we eat him up into, merge that phagosome with the lysosome that has the bad killer chemicals in it, digest it, and within about 30 minutes, you can destroy bacteria in that phagolysosome fusion vesicle. And that is our destruction step. And then we will excrete out any waste that we have produced from the process. So that's the whole process of phagocytosis. And in that part where we have the destruction and excretion, this is probably, as we learned in chapter 16, one of the most important steps that we have as far as then calling in your, adaptive immune response. So your B cells and your T cells, your bombers and your tanks in the immune response. So this crap that they leave around is what the macrophages ultimately are going to pick up and say, thanks a lot, neutrophils, you're making a mess, but now we can identify our enemies even more specifically and target them specifically. And we can hone our bombs in to those enemies specifically because you left around this crap when you destroyed these bad guys. So they will pick up those guys. And again, we'll talk about it in chapter 16, present them to our bombers and our tanks, but through approval of the captains, right? We got to get a captain approval first. We'll get into that. But anyways, so we're there. So all of that stuff is going to be mediated by our cytokines. These are just chemical signals produced by cells in the area that were initially involved in the sickness. Meatball. No, I put up the gate for a reason. Don't try to squeeze in. Anyways, cytokines or chemokines, however you want to look at them, they're chemical signals made by cells either in the injury area or cells that have migrated into that area, like the neutrophils. They can still migrate into that area. They can eat things up, but still also make more chemical signals asking for specific kinds of, backup, essentially. That's what our cytokines are going to do for us. These can control the inflammatory response, blood flow to the area, and activation and growth of our lymphocytes. We have our signs of inflammation, our Latin terms, which are our rubor, calor, tumor, and dolor. Rubor being redness, calor being warmth, like you burn a calorie and it gives off heat energy. That's literally what a calorie is a measure of heat energy whenever you burn like a gram of carbohydrate or something. I don't remember the exact term. Don't tell Dr. Shim that. Okay. Then we have, or Dr. Singh, but we all know that Dr. Singh would be nicer about it. So we have tumor, which is swelling. Then we have dolor, which is the pain of it. And then you may also have loss of function associated with the inflammatory response as well. Think about whenever you hurt your back. So when you have a lot of pain and swelling and everything like that, the loss of function, it can be part of that. So we know that because if you hurt your back, if you throw out your back or something like that, goodness, you might not be able to function as a result of the inflammation from that. So that is a thing as well. It just doesn't have its own little Latin term. So this is all on purpose, though. It all has its use. We're going to attract immune components to the area, initiate tissue repair, isolate anything that was harmful brought in with the injury or infection, including any toxins, and destroy and block any invaders that came in or could be coming in, or we don't want them to spread to other areas either. So all of that's going on just as a response with your inflammatory, signaling. So all of that's happening from that, and that's not even including our chapter 16 stuff. So that's just the innate response. So every time that we have our tissues, like our neutrophils, moving into an area, they're going to be squeezing in between those cells in your capillaries. That movement where they squeeze from the bloodstream through your capillary cells, like in between their junctions, which is crazy to think about, but they literally squeeze their own cells between those cells and then into the tissues where they can move around from using that, mononuclear phagocyte
Which
system.
one we're going to?
Patient entrance from Mercy,
Yeah.
They'll be able to get there via
Surgery center.
squeezing in and moving in between those cells. That's going to be called diapedesis. So remember that you can
I don't know how.
move that way. Guys. Nope. No offense. All right, here we go. So we have the movement via diapedesis into the tissues from the bloodstream. And then that's also going to, that's all called by that cytokine action, right? Calling everybody to the tissues, moving via diapedesis into there. Now our neutrophils can start eating things up and leaving their destruction, their excretions from the destruction behind in the tissues for the macrophages to pick up and deal with that later on in our next part, right? And also during all of this cytokine production, we have signals for producing fever. Not always, of course, but when we do have signals for fever, these signals are called pyrogens. And like a pyromaniac likes fire, pyrogens are dealing with heat in your own body. So we're going to increase the temperature in your body because of these chemical signals. These can be induced, like a pyrogen, something that can induce your fever. A pyrogen could be parts of a pathogen, things like, the presence of LPS is a very potent pyrogen. It signals for the production of fever just by being there. So that's what we would consider an exogenous signal. Endogenous signals for pyrogens, those are going to be signals sent by your cells. So whatever they're reacting to in the area, whenever they see this thing or that thing or another thing, they're going to produce more cytokines, go figure, that are going to help initiate the fever response. And those then were going to be endogenous pyrogens. So another chemokine or cytokine that you can be familiar with that I felt like was the one that was, I think, a little interesting, but it has very great innate function for our cells, was going to be that interferon. That's the call from your buddy letting you know that he's being, burgled or whatever, getting attacked. I am, getting attacked by somebody coming into my house and killing my family members. I'm going to try to get a call out to my neighbors to let them know what's happening so that they can have their shotguns ready. That's what interferon is, to interfere on the viral plan. So that instead of letting me get infected with a virus, getting infected and getting my house all destroyed by an invader virus, my buddy called me and let me know what was fixing to happen so that I could be prepared for it. And that call is interferon. So we can start making antiviral protective molecules to keep from having any sort of infective, problems. So whatever. So we have the complement cascade, and the complement cascade is just a whole bunch of proteins that are always in your blood. You don't need to be activating the production of these. They're just always there. And they will be triggered by the presence of, down 3 pathways. We know this, right? The classical complement triggering pathway is going to be triggered by antibody being present. You have antibody binding to the surface of the measles virus. And when that happens, it triggers the complement cascade, and that will poke holes in the virus. And then now it doesn't work like it's supposed to, that sort of thing. Of course, we'll work with bacteria, maybe even more effectively in that regard. Also can be triggered by certain sugars on the surface of bacteria. Those sugars are recognized by a molecule in your body called lectin. And when lectin is bound to a sugar, it triggers the complement cascade just the same way. And then the alternate pathway of the complement cascade is going to be triggered by repeating molecules like lipopolysaccharide, similar to how the PAMPs work, but we're not being recognized by, PAMPs aren't being recognized by cells here. In this case, we're talking about basically complement cascade proteins recognizing the patterns instead. And those proteins see the patterns, and then they trigger the complement cascade, just like the other 2 pathways would. It's just a matter of which molecule is starting the pathway. So now that we've started our pathway, all of our intermediates some of them can have functions. Some intermediates help with the inflammatory process, which we already talked about the benefits of that. And some intermediates are going to be involved in opsonization. And opsonization is when you add something to the surface of a pathogen to make it easier for your phagocytes, like your neutrophils and your macrophages, to eat up the bad guys. And so that's opsonization, helping out phagocytosis, making it more effective. And then ultimately, of course, the big daddy goal of our complement cascade is going to be the membrane attack complex. All of these cascade proteins, you activate this protein first, and then it leads to these proteins, and those proteins cause these proteins to be made, and down the whole line once you trigger it. The end products can come together and build a hole in the surface of the microbe, and then that causes its contents to leak out, and digestive enzymes from nearby cells can get in easier and destroy the pathogen much more easily. Complement is great because you always have it in your blood at all times, and it's always ready to go. It doesn't rely necessarily on cellular response either, so it can be a really useful way. of dealing with things. So I forgot to mention when you were talking about inflammatory response with the fevers, about the benefits of fever just by itself. So just briefly, remember, fever is increasing your temperature, which is sometimes going to make it harder for certain microbes to be able to multiply. The signals for fever and how fever operates also, it hoards away your iron so that the microbes can't use it, and they need iron too in order to live. So that keeps them from growing. And also, because of the temperature being high itself, it decreases the enzyme activity of the microbes so that they can't function as well. So it's part of that. It increases our cellular metabolism, our own cellular metabolism. It increases it so that we can function faster and better, deliver signals more effectively, and increase the growth of our lymphocytes, which are going to come in chapter 16. Oh, so that's chapter 15. We've laid out this whole concept of everything that is going to start off a response to an infection so that we can keep everything under control until the chapter 16 guys come. So we've got all that laid out. We've got inflammation working for us. We've got fever working for us. We've got complement working for us. We've got our phagocytes eating things up and pooping out their excrement and leaving that all around for our macrophages to find. And we're moving around in the fluid that we're, bringing with us, creating, edema is whenever you have fluid buildup because you're moving the cells into those areas. The only way you're going to get rid of that fluid is by moving that fluid out via the lymphatic system so we can filter through the lymph nodes. We've already learned about how important it is to filter back through those lymph nodes because we learned about how we have our cells, like our B cells, waiting there to check every passport of everything, every single thing, not just cells, but even molecules going through the lymph, making sure that you are self and you are not foreign. And so they're going to get filtered through our lymphatic system extremely efficiently on the way to rejoin back up with the bloodstream so we can get that fluid reincorporated. So we aren't having buildup of fluid in your extremities, but all of that has to be pumped by your muscular system. So you're walking around, moving that fluid back into your system. Now the cells that are still there can keep fighting the good fight, and we can keep moving new cells in as needed, but also recycling back out that fluid the entire time, all waiting. All of this happening, doing the best it can, waiting for chapter 16. Okay, so we're there, we set it up. So chapter 16, now that we've got all of that set up, we've got our phagocytosis going on in our inflammation, all of this. The overall goal of chapter 16, that's our adaptive immune response. We want to completely eliminate the threat, that specific threat, without damaging any related tissues nearby. But we also want to create memory so that if we ever see this again, we don't have to go through this whole waiting process and reactivating and calling up the correct captains. And once the captain is activated, he has to activate the right B cell, the single B cell that matches up with this thing, and the single cytotoxic T cell tank that matches up with this thing. And everybody has to multiply out and then differentiate and all of this stuff. In your memory response, all of those things already happened, and we're saving the product of those things, minimal amounts of those products, but enough that whenever you see it the next time, you can just crank out IgG, your workhorse antibody, instead of waiting on IgG to form, where you initially, with your B cells, with your plasma cells, when they're activated, will be cranking out IgM. Who needs that? I mean, it works up front and it's the easiest. It does a lot of fast work, but it is not as effective as IgG. Considerably more effective, stronger binding, more action, way more protective, better memory response. IgG is what your goal is, but you can't make it at first because it's just not as efficient to start out that way. Your naive cells need to be stimulated accurately in order to switch to IgG. All of this takes time, and we know that it does because whenever you've been sick, it takes you a week or so to get over things. How strong your response is to a pathogen determines how quickly that can happen. Where in the body this is happening can determine how quickly it can happen. And whatever signals, those cytokines that you're getting, also help determine how quickly it can happen. all of those factors have to be playing together in order to get an appropriate immune response. That's why there's so much variability in how long it takes for you to get over being sick with something. So, and it also is what kind of determines why, when you get the COVID vaccine, you get the vaccine and you're not getting as sick, but you're still going to get sick with COVID. Now, some people don't, but if you might be the person that you've had, a lot of people have had the vaccine. I had the vaccine and then I got COVID. I had the vaccine and then I got COVID and I had that freaking 104.5-degree fever that I had to take 2 ice baths. This was after I'd taken Tylenol to lower my fever and everything. So that's with my vaccine. So why are you still getting sick? If you got the vaccine that you're supposed to react to it, imagine what would happen to you if you hadn't had the vaccine. You have enough protection there to keep you from dying because of your vaccine. And that's why people aren't dying anywhere near as much, even though COVID and the strains of COVID that we have now are actually deadlier than the ones we started with. And that's not a lie. They are more infectious and they are technically have more of those virulence factors than the previous strains did. But we have the vaccine now to help us overcome the infection more quickly. But the antigenic response that we need in order to keep it completely away, like we see with measles and mumps and rubella, MMR vaccines, that work so effectively, you never even know you saw the thing. They have a better antigenic response and elicit a better protection than the COVID vaccine. But hey, are we complaining? This is what we have. We have some protection. And now look at us. We can have class in person again. You don't have to stay 6 feet away from every single person on the planet and even worry about it when your spouse comes home from having worked at the hospital that day. So things have changed. And that's thanks to these vaccines. Will be great. I'm sure at some point we'll have vaccines developed that will work more effectively than that, but we're certainly thankful for what we have. Anyways, coming back to the whole point of this, that's what memory is for. That's the goal, right? And that's what your body wants for you when you're exposed to something naturally as well. So yeah, we already talked about all of your lymphocytes, include all of your leukocytes, all of your white cells, and even your red cells. Any blood cell, it all comes from your bone marrow. That includes our lymphocytes, which are our B and our T cells. Your T cells mature in the thymus. And then your B cells like to hang out in your lymph nodes and in the lymphatic tissues, whereas the T cells, they'll hang out in the lymph nodes too a little bit, but they prefer to circulate more than the B cells will, simply because they're going to be like those captains looking out for whatever potential any cell at all could be interacted with by your cytotoxic T cells. So that's why they like to circulate. And your captains are always looking for wherever that antigen might be, come into contact with it with a macrophage or whatever other antigen presenting cell could be presenting to it. So that's the idea with that. All right, so lymphocytes will be, I know, there's a package. The UPS guy also knows there's a package. You don't need to tell him. I'm getting boots today, you guys. I'm really excited. I think that's my boots. So anyways, lymphocytes, they'll be activated whether you're a B cell or you're a T cell. However you get activated, and we'll talk about that, how that happens in a moment, you're going to proliferate and then you're going to differentiate. First you proliferate and then all those clones that you made up, then they're going to get their assignments on whether they're memory, regulatory, or effector. So those are our 3 things that you could have. Remember, there's going to be 3 roles. Whether you are B, T helper, or the cytotoxic T cells, it doesn't matter. When you see the thing and you get activated, you proliferate, and then you're going to assign your troops to be either the memory, effector, or the regulatory. All right, so this whole process, your body went through all this genetic reassignment, this genetic recombination of your genes to make up this variability so that you can respond to all these different antigens, the 8.6 billion, right? And now we've got to go through clonal selection. So clonal selection, it involves several parts. First, you have getting rid of the cells of those 8.6 billion possibilities, getting rid of all the ones that have sorry, the dogs, they have this squeaky toy. I like stacked up the little beds that they lay on so I can wash them, and they're still laying on them, of course. But there's like a squeaky toy under one of them, and it is like this loud, it makes this sound. And every time they get on the bed, it makes this noise, and they all always look confused. It's just stupid. I know, Spaghetti, I hear you. So, he's crying now. So anyways, right, moving on. Clonal selection. First, you go through clonal deletion of the ones that see self. You don't want those guys. Now you have this whole repertoire of the rest of the cells that survived, the ones that had the 8.6 billion cells that you had that could identify anything. Got rid of the self ones, the ones that are left over that don't react to self, hopefully. Each one cell reacts to one epitope, right? One part of an antigen. They react to one very specific thing. This particular shape on this potential protein that you just might see at some point in your life is just waiting out. And once that, part of the fidget spinner, like we said in lecture, once that part of the fidget spinner or that portion of the spike protein of COVID shows up and you interact with it, you get activated. That one cell, once it sees its part, gets activated and it will proliferate, like we said, and then assign the troops their roles of memory, effector, or regulatory. That's the differentiation part. So that's how it's always going to go with any lymphocyte. That process is called clonal selection. All right. So that's how everybody does it. I talk about epitope. An epitope is just a part of an antigen. What is an antigen? Anything that your immune system could have an immune reaction to. The spike protein on COVID, for example. This particular antibody, its variable region, the portion that interacts with the antigen, the variable region recognizes a part of that spike protein called the epitope. So that's where we're dividing those up even farther, okay? So the epitope is the part of the antigen that we are reacting to. That antigen, if we can react to it with our immune system properly, we have a cell that could potentially have a reaction with it and create this whole thing to happen. That's now called an immunogen. We don't need to distinguish between the two on our exam, okay? Antigen, immunogen, exchangeable. So we can see this as foreign. We react to the part of it called the epitope. Some things are just too small for us to react to. It's just not big enough for our protein to engage with it because it's just not big enough. So what we can do is add something onto it called a carrier so we can react to it properly, or stick another one that's too small onto it. So now we have all these different regions that we can actually interact with and get a handle on to create antibodies against those parts, so that when you see those individual pieces by themselves, we've already got antibody now that can interact with it appropriately. When you are a receptor on a B cell, your IgD, right? That's our receptor version of the antibody. It's on the actual surface of the cell, trying to figure out how to get activated. You don't bind as specifically and as tightly and to tiny little things the way that maybe IgG can. IgG has that more specific binding. So when it does see the tiny thing after you've activated your B cell and it has interacted with this hapten, the small piece attached to a carrier, right? That's the only way we can interact with it when we're naive and we make our IgM, and the IgM, it will start to be more specific and interact with just the hapten, not needing the carrier anymore. It's more specific than the receptor is. So we've identified that epitope, and now we can focus on just that epitope and not needing a bigger molecule to support it behind it. So that's why it happens the way that it does, and why you only need the carrier during that initial response. It just helps aid the presentation process and the interaction with the other molecules. Okay. Antibody doesn't need it after that. So anyways, alloantigens, this is anything on your body that my body would see as foreign, but it's normal between us, generally speaking. So blood groups, I have a blood group and you have a blood group, but your blood group, if it's not the same as mine, that could cause rejection. So that's an alloantigen, but we both have blood groups. The bigger one that we talked about, right, was MHC, especially MHC1. You have 2 MHC molecules available in this whole adaptive response. The MHC1 molecules are present on all of your nucleated cells. All of them can use that as their red flag to hold up and say, I found the part of the alien that's in my chest. I have alien in my chest, come and kill me. I don't want it to burst out. So that is MHC1, stuff from inside, right? The call came from inside of the house. The alien came from inside of your chest. If it's inside, MHC1, the one looks like an eye inside. MHC2, that will present molecules that are antigen presenting cells picked up from outside. Turns out that our macrophages and our dendritic cells, which, remember they differentiated from monocytes, they're phagocytes. They go out and pick up the excrement from. I understand I'm doing that right now. My Alexa thinks it needs to tell me that I'm having a review session with you guys. Anyway, so
starts in 15 minutes.
Anyways, moving on. So we're walking through our whole process here. Antigen presenting cells pick up things from the outside, and often that can be the stuff that the neutrophils that got to the site first. Remember, they're the most numerous of your leukocytes, your white blood cells. So they get there and they just eat things up and excrete it out after they digest it. So they're phagocytes. They leave their trash around. The macrophages, they're also phagocytes. They can eat up the bad guys too, but they're also going to pick up the neutrophil trash. So they're picking these guys up from everywhere. They say, I found this stuff. It looks like it's part of an alien. This could be a problem. Found it outside. Does anybody know what this is? Those are our antigen presenting cells. When they pick it up from outside, they put it on their MHC2 markers. This is important because your MHC2 markers are the only ones that your captains can identify. Captains don't give a, flying fart about your MHC1 presentations. They don't care, can't see it, don't want to have anything to do with it. Your captains can only be activated by something on your MHC2. That's the whole point of the MHC2. MHC2 only interacts with your captains. That's your T helper cells. They're not interacting with diddly anything else. So your antigen presenting cells, including your macrophages and your dendritic cells that are going to go eat up the stuff from the neutrophils, they can interact with your helper cells. The helpers being the captains. The captains are going to help start this immune response going, the adaptive immune response. You also have another antigen presenting cell, the B cells. The B cells are not true phagocytic cells. They're not going out and eating just stuff up from areas and whatever. What they are doing is, we already know you're bringing on all that fluid from your injury site or your infection site and putting it back into your lymphatic system. Well, they're waiting in those lymphatic tissues. B cells are just sitting, waiting. They are waiting in the hangars, those hangars being your lymph nodes and your lymphatic tissues, hanging out in those hangars, just waiting to see the piece of the alien that it recognizes coming through. That specific part of that alien, I need to see it. And when I do, I'm going to be, well, look at this, Captain. Look at what I found. So your B cell with its little, IgD antibody looking receptor recognizes the piece of alien on its little IgD antibody looking receptor variable region, sees that, and then can put it onto MHC2. When that receptor sees what it's supposed to, it goes inside of the cell, switches it over to the MHC2, and what is going to interact with it then? If it's on MHC2, your T helper cell. The only thing that interacts with anything on MHC2 is the T helper cell. And the T helper cell will not do anything until it sees something presented to it on that MHC2. Now, MHC2 in general could present anything. So if you're an antigen presenting cell, like a macrophage, you don't pick up things specifically. You're just picking up whatever and putting it on your MHC2. Your B cell, though, it recognized that specific part of that specific alien and that antigen and saw it with its little antibody receptor, our immunoglobulin receptor, IgD. Then when it reacted that way, said, I see this specific part of the alien. I need to go find the captain that also attacks that specific part of that alien, puts it on the MHC, and interacts with the T helper cell. Whoever it is that's presenting that part of that alien on MHC2, whether it is macrophage or whether it is your B cell, your T helper cell is the only one that sees that. The T helper cell comes over, says, I recognize this antigen, this part of the alien that is being presented correctly on our MHC2 molecule. They picked it up from outside of their cells. I am going to recognize that as I am a T helper cell with my CD4 molecule. My CD4 says, yep, that is in fact MHC2. My T cell receptor says, yep, that is in fact on the MHC2. That is the antigen that I recognize. It recognizes that with its T cell receptor, okay? And its CD4 recognizes that it's MHC2. Now that we have that verification going on, I, as the captain, give you the B cell that's presenting it to me, or you, the antigen presenting cell, signals to activate and go fight the good fight on your end, whatever it is you do. And you send me signals now because we interacted, saying that I can start the war. And so I'm going to, as a T helper cell, now that I'm activated, what's the first thing we do? Proliferate. Then we differentiate. So we've proliferated. Now we're going to get our memory and our regulatory cells. Great, cool, they're off, whatever. And our effector cells. As a T helper cell, you have two kinds of effector cells. You have the Th1 and the Th2. The Th1 response, our Th1 cells, they still interact. They still themselves have to interact with MHC2. Okay, that's what they do. However, the Th1 cells are going to be interacting more with what I call the MHC1 response. So your Th1, even though they're helpers, that's always going to be CD4, that's always going to be MHC2 activation for themselves. They now can go and activate our CD8 positive cytotoxic T cells. Remember, CD8 positive, CD8 is going to interact with MHC1. So that's why I call that the MHC1 pathway. So CD8 recognizes itself, MHC1. The T cell receptor on the cytotoxic T cell, your tank, the T cell receptor on that recognizes the antigen being presented by MHC1. So that part of the alien that is being presented from inside of the cell. Oh my God, I have this alien in my chest. Here's a piece to prove it. Help me. The cytotoxic T cell sees that MHC1 holding out that piece of the alien. Its T cell receptor sees the piece, says, I recognize that specific antigen. Its CD8 molecule recognizes that you're holding it out on MHC1, verifying that it came from inside of your cell. And now I can kill you because I got that signal from the Th1 helper cell, which was differentiated from the activated T helper cell. It was just T helper at first, differentiated into Th1 and Th2. The Th1 is the one that's driving this response now. Okay. Now that I've seen you as a CD8 positive cytotoxic T cell with my receptor and my CD8 cell is verifying that, my CD8 marker is verifying that. Now that I've also been activated by my Th1 cell to give me the go ahead, that's my captain. Now I can make my perforins and my granzymes. My perforins poke holes and my granzymes are going to digest the things inside of the cells via getting in through those holes. That causes us to our cells that are infected, or self cells, to digest the stuff that's on the inside of them, and eventually they will die, eventually going through apoptosis, which is the cell unaliving itself. Okay. Great. So that is that side. That's the Th1, CD8, MHC1 kind of side of things. Whenever we activated our T cells, Remember how like we could have activated it with our macrophages or our B cells. It doesn't matter. Your B cell, if it picked up that antigen with its little IgD receptor, brings it inside, puts it on its MHC2, presents it to our T helper. It's just a naive, generally speaking, T helper, activates the T helper and so that it'll proliferate and turn into memory and regulator and its effector cells, which are Th1 and Th2. We went Th1 already. So now it's Th2's turn. Th2 sends signals to B cells to activate them. Th1 does not do that. Th2 sends B cells signals to activate them so that they can turn into plasma cells and crank out antibody. That's the main role of a Th2 cell. So Th2 cell has more of that role in that MHC2 response where we're responding to things outside. So that's why they're divided out that way, okay? Regulatory cells, B or T, whatever kind, they are going to just help the immune system stay under control so we're not overreacting. We don't want any autoimmunity to develop, and we don't want to over respond and destroy tissues that aren't infected. So that's what regulatory cells are going to do. Our B cells, when they are activated, again, they make memory and regulatory and effector cells. Our effector cells for B cells are called plasma cells. They make antibody. Antibody is just protein that is being secreted by those cells that will go out into the bloodstream, stick onto those antigens, and then do their job. And so what are the jobs of antibodies? They neutralize, that's binding to specific markers on the outside, like the spike protein, so they can't interact with their targets. We can coat, that is just covering the whole surface of the bad guy, so they just can't in general do anything. We can opsonize, that just means we're providing a handle for the phagocytes to grab onto when they're eating up the bad guys, helping out phagocytosis. Agglutination, causing the bad guys to stick to one another, because if they're stuck to one another, just like your red blood cells can stick together whenever you have clots forming, our antibodies can cause bad guys to stick together in that response. So they can't do what they're supposed to normally do. We have activation of complement. Remember, that was the classical pathway we learned about in chapter 15. That's going to help with the inflammation response in the immune response, the innate response. It's going to help with opsonization in a different way. The complement proteins can help with that. And we have the membrane attack complex poking holes in the surface of the pathogens. And then we also can have antibodies that interact specifically with the toxins themselves and not with the pathogens. So that's what the antibodies are going to do. And of course, like we said, you always start out with the IgM. It is a pentamer. It looks like a snowflake. It's 5 antibodies essentially stuck together by their little handles, the long end of the Y. That's the constant region. These antibody types, IgG, IgM, IgA, IgE, IgD, all of these are determined by that constant region. So the constant region doesn't change a whole lot except between the class types. The variable region, where we actually have the binding of the epitope, the antigen, that's at the ends of the Ys, the tops of the Ys, that part can change so variable that we reassort our genes, adding in and removing nucleotides to give all this variability. That's where our 8.6 billion different possibilities come from in that variable region. That's in the part of the antibody called the FAB. FAB, the AB, if you notice, you have variable has an AB in it. FC refers to the part of the antibody called the constant region, C for constant. Okay, just think of it that way. And the constant region determines whether it is IgM, IgD, Ig, whatever. Okay. And the variable region interacts with the antigen. So that's where we get these different things. When we start out with IgM, that's because that's the type of constant region you have. As the cells are interacting, getting signals and affirmation that they are interacting correctly with the antigen, then we switch from IgM to the other types based on whatever signals we're getting. And IgG is our workhorse. If we want the most of it, it's usually going to be 80% of your antibody response. And it is the hardest worker. It can do the most. It is the most important in your memory. IgA is the one that works best in your mucosa. It's a dimer, and it just happens to work best in those kind of sticky mucousy areas. We call it secretory. Then we have IgE. That's a type of antibody that's associated with allergies and usually was adapted for parasitic infections. And it's just we don't have those in the United States really anymore. And then we have IgD. which is the receptor one. So that's the one that's on the surface of the B cell before it's getting activated. Okay. All righty. If you want to measure somebody's immune response, you can do that by measuring their antibody concentration in their blood, that antibody against HIV, for example, like we learned with ELISA. The darkness of your ELISA color change can be used to measure the concentration of the antibody present in the sample. And that can give you basically a measure of the titer or the concentration of that antibody in that person's bloodstream. Every time you see something new and you react to it at first, that's your primary response. Of course, all of this crap of activating captins and B cells and cytotoxic and whatever, proliferating and then differentiating, and then going out and doing your job and potentially even class switching your antibodies. All of this takes so much time. Oh my gosh, that's your latent phase during your primary response. So that whenever you get to the second response or any response after that, the amnesiatic response is always going to be faster. We don't have to go through that whole process. We have our memory cells there to just kick into. All right, then we have all these different kinds of immunity, natural and artificial, active versus passive, right? Natural is anything you see in nature. Artificial is going to be anything that is introduced by a medicine. Active is something where you create your own immunity against it, and passive is where we are giving you immunity from maybe somebody or something else. Okay, so you get antibodies put into your body by your mother whenever you're breastfeeding, or you get antibodies put into your body whenever you go take Humira or get a gamma globulin infusion. Or I just saw a commercial, literally, I was watching last night. If you guys want something super wholesome and super chill, and you want to see literally the most wholesome, chill cooking show of your entire life, you need to get on YouTube and watch Townsend's. I'm not kidding. Townsend's. And it's this guy who does cooking from like colonial America, and he dresses up and everything for it. And he has this little like cabin that he built that is like all like colonial America era. And it's just literally the most wholesome thing you'll ever see. And if you haven't, in that and Max Miller, if you've ever seen Max Miller Tasting History, those are literally the most wholesome things you're ever going to watch in your life. And they cook and you learn about history. Watch it if you need to chill. I'm not kidding, but I was watching that and this commercial came on for this something MAB. I don't know what it is. Who knows anymore? And it had a name also that is also confusing. Just Humira is something I feel like is easy for me to remember. That's why I always remember that one. But then there are other ones like Remicade, and that's a lot like Humira. And some other ones that are like that are all something blobbity blobbity MAB. And, Humira is adalimumab. But I've never taken any of these drugs. That's just the only one that sticks in my mind. But there was one that came on for a new one, and it was something MAB, and it was something Lumab or something, and it was a monoclonal antibody, which is what MAB means. Okay, anytime that's at the end of a medication's name, it's going to be a monoclonal antibody. So you're putting antibodies into your body to block something, and in this case, it was for allergies. And it's probably be more pertinent when we get into chapter 17, but it was an antibody that blocks IgE antibodies. And IgE antibodies are the ones that drive your allergic response. They're acting against things like pollen and dander and things like that instead of parasites, which they normally would. And when you make these IgE antibodies, they stick onto mast cells, like the little receptor end of it. And the mast cells like to pretend like they're B cells in a way like that. So the IgEs bind to the surface of the mast cells. And when the IgE binds to dander, let's say pet dander or pollen, it signals into those mast cells to release mast cell crap. Mast cells release things like histamine. This should sound familiar. Yeah. Anyways, that's how our allergic responses work. And so they always hang out like that, the mast cells with those freaking IgEs on them. And what this antibody claims to do that you can get to treat your asthma, because asthma is an allergic response, you can get these shots with this antibody that blocks IgE and therefore blocks the mast cell's ability to discharge its histamine response. And so one of the risks that they have, of course, on there is please tell your doctor if you have any parasitic infections. So that should start to make sense to you guys why they would say that on that commercial. And I thought it was just so pertinent that we just were learning about this. And I just saw that commercial. But anyways, so that's a thing now. Yeah, you know. So that's going to be artificial, passive. Anytime you have those put into your body. Cool. So the whole point with vaccines is to help stimulate that primary response and to avoid having to go through that, latent phase, so that when you see something, which is for real in the first time, but your body thinks it's the secondary response. And so amnesiatic response, you can have a very strong reaction. We want to give it as much chance as we can. So we'll sometimes put things in there to help it stick around, like in your arm or whatever, and to help elicit a better response or whatever. Those are called adjuvants. So anything added to the vaccine to help with that is an adjuvant. Of course, we have all these different kinds of vaccines. I'm not going to go over them again, but whether it's the whole or the part, and then however we're going to give it to you with a shot in your under your skin, in your muscle, or whatever. That's the different kinds that we have. So it's all the same immune system that you have, that you would be reacting to the actual disease. It's the same freaking immune system. It's not doing anything different. So yeah, we talked about the misinformation. I'm going to move on. I know this is going long, but I'm hoping that explaining all this stuff, because chapters 15 and 16, you cannot tell me that this stuff isn't important in every single aspect of somebody healing from any sort of illness. So if you're going into, I don't even care if you're going into nursing or if you're going into veterinary, and even dental has a lot to get out of this, because we're talking about the immune system dealing with any foreign invader in any creature ever. Our immune system isn't exactly the same as, like, say, a dog's or a horse's, but they all have the same concept here. So it's important. And this stuff is happening even whenever you're not having an active infection. When you're injured, your immune response is happening, right? So let's go over our missed concepts. I don't know how people have issues understanding about our, first line of defense, but apparently they have in the past. This is your physical and chemical barriers. Probably, and I don't remember off the top of my head when I made the slide, okay, but it's probably referring to lysozyme and keratin. Please remember that lysozyme is the enzyme that breaks down peptidoglycan, and keratin is the waterproofing protein in your skin and is also in your hair. I know, but I'm not going to ask you about your hair, okay? I'm asking you about the waterproofing part of your skin. Obviously, physical barriers include your skin itself, the hair on your skin and in your nasal cavities, any aspect of your skin where we might have antimicrobial peptides can also play a role in that. You have your mucous membranes. The mucus itself has a flushing activity. Any fluids in your eyes, tears like that can literally wash things away. When you blink, it pushes things away. We have the cilia moving mucus out, and all of this. The chemical barriers will include things like saliva that has lysozyme to break down the cell walls. We have tears that also have the lysozyme and other antimicrobial things. The acid in your stomach, the sweat, and that has salts in it. Skin has salt on it. It's harmful to a lot of things. We're learning that because it's a selective agent in our selective and differential media. And then we have our normal flora that takes up all of the seats in the area, and also makes, like, things to keep things away, changes the pH, takes away the nutrients and whatever else. So we have that stuff. So I says there's a mnemonic here that they say is salt and mucus, and maybe it stands for something, and I don't really remember what it was, and I don't know if I even really care that much. So let's see though. I did. It's a whole thing apparently. Salt stands for skin, acids, lysozyme, tears. Mucus stands for, obviously, mucus, understanding the role of the mucus, chemical barriers, up being the movement of the cilia, moving the mucus up, and then skin, of course. It said we repeat that one to emphasize the importance, but also to make sure we're spelling a word that actually makes sense to you guys, but it also in it itself. Dang it, I did that. Sure. Sorry. Anyways. So here's our questions for this concept. Which of the following is a primary function of mucus in the respiratory tract? All right, so the primary function of mucus, of course, you're going to be trapping things, and then you can get rid of the mucus and expel it from the body, right? So we can trap it before it gets down into the deeper parts of your lungs, where you're more likely to have it transfer to other parts of your body. So we want to keep it out of that part, and we don't want to get pneumonia either. So does it provide energy? No. Does it enhance the absorption of nutrients? Let's see, by the way, does it enhance the absorption of nutrients? No. Does mucus increase the temperature of inhaled air? No. What it does is trap stuff so we can cough it out and it doesn't get deeper in our lungs. Which of the following conditions might compromise the first line of defense, increasing the risk of infection? Okay, so first line of defense, this is your physical and your chemical barriers. This is not your cells that are sending signals to one another. This is not your B or T cells. This is just like skin and things like that. So does regular exercise and a balanced diet increase your risk? No, guys, that's actually going to make you a lot healthier. The number one thing, if you have anything wrong with you, that your doctor is going to tell you is, are you exercising regularly? Are you eating healthy? Because these things are important for absolutely everything in keeping you healthy. Of course, we all know we could probably do better on both of these, but we all know better. So then we have the chronic use of corticosteroids leading to thinning of the skin. Uh-oh. That's getting a little bit specific. Y'all using some corticosteroids on your skin? If you have ever used hydrocortisone itching cream, that is a corticosteroid that you put on your skin. You can also take steroid medications like prednisone and whatever orally. These things are detrimental to the function of your immune system because the way that they work is by inhibiting your immune response. You really do not need to be taking those things unless you need those things. Use your hydrocortisone cream on your mosquito bite for a day or two. If you're using something like hydrocortisone cream on your skin regularly because you have a repeated rash or you're using it on large areas of your body, go to your dermatologist, please, and deal with that problem at its root. Don't keep using hydrocortisone cream because it will absolutely lead to thinning of the skin. And if your skin is thinning, you are more likely to have microbes invade your skin and then cause infection. That is a terrible thing to be doing to your skin. Terrible thing, increasing your likelihood of getting an infection because of medications. How many medications, I wonder if we take, because I was just thinking about this the other day, that are causing so much damage in your body, and how much are they really helping? And when is it time to talk to your doctor about the benefit versus the risks? I'm not making that decision for you on any of your medications, but always think about that. If there are side effects to your medication, are these risks worth it for the benefit? And steroids and any steroid related medications are absolutely number one, the least understood by patients as far as the negative side effects that you will be having as a result of them. Steroids are terrible for you. Number one, I promise you, if you have, bronchitis and you need to reduce that inflammation to help you get over the illness, take the steroids. But if we are just throwing a steroid at every infection that you have and every inflammatory response that you have, you're just decreasing your body's ability to deal with infection and causing other side effects like weight gain, weakening of the skin, and other things that can have more long-term effects beyond that. So please be sure that you are having these discussions with your doctor. Are we sure that this steroid is necessary, or is it just for my comfort? Because if it's not actually helping you recover and it's just for your comfort, maybe reconsider. Just saying. Okay, adequate hydration and good sleep and hydrating. No, we need that. That's not going to be a problem. And then frequent hand washing with soap and water. You need to be washing your hands with soap and water so you can remove microbes. If you do it too much, you can remove the barrier that could be protecting your skin. So there's a line there. But really, it is talking about the obvious one here being if you're using steroids, that'll lead to the thinning of your skin. That's a very direct way of compromising your first line of defense. Obviously, A and C are helping your first line of defense. D should be helping your first line of defense as long as you're not overdoing it. When I worked at any of the labs that I work with, I'm sure you can imagine, labs typically where I am going to be wearing a lot of gloves and washing my hands. If you guys are going in the healthcare industry, if you're not already working in the healthcare industry, then you would know if you are wearing gloves for long periods of time and washing when you're having to change gloves a lot, your hands get so dry so fast. And this is actually going to make you more susceptible to skin infections. So then D does come into play, but you just have to, you know what I'm saying. Right, for chapter 15, we also have the benefits of the fever and what the fever can be doing for you in your body. I'm not going to go through every bullet on this because it is going on a little bit, but like we also have talked about this before, but here's a little bit more detail on it if you wanted to read into it. My little mnemonic for this one was fire up immune healing. And of course, this is talking about, inducing that whole inducing the fire, your fever. Fever is the F part of that, and it all stands for a thing. In case you haven't been paying attention, I have in that little notes section, which I can pull up here, what all of these letters stand for. And I know I've been going over them, but I don't want to do it right now because I feel like you can read. And it kind of makes sense. So fire up, y'all. You want to get rid of the microbes. So we're going to increase your temperature with a fever. All right. Which of the following is a benefit of fever in the context of infection? Does fever decrease the production of white blood cells? No. It's actually going to increase because of that increased temperature increases your metabolism. Does fever enhance the ability of immune cells and speed up the healing process? Absolutely. It increases your metabolism, and so it speeds up everything going on. Fever increases the ability of the iron in the bloodstream, promoting the availability, of the iron in the bloodstream, promoting pathogen growth. It does not. It does the opposite. It decreases the availability of iron in the bloodstream and then decreases pathogen growth. And then fever decreases the body's metabolic rate, slowing down immune responses. Like we said, it's the opposite. It's increasing your metabolic rate and therefore increasing your immune response. In a clinical setting, why might a fever be a significant indicator for a healthcare provider? Obviously, and this is obvious, right? If you have a fever, it indicates that you have an inflammatory response of some kind, not necessarily an infection, but often can be associated with infection, which you can have fevers without infection, believe me. So you've got a fever. What does it suggest? It suggests a patient has a cold, which requires immediate antiviral treatment. It indicates the presence of an infection or inflammatory condition that may need further investigation. Thank you, choice. What an intelligent choice you are. So if you had a cold, might you have a fever? Potentially. That might mean you need antiviral treatment. But does the fever tell you that that is a cold and you need a virus? Nope. It tells you there's an inflammatory condition, which may be an infection or not. You might need to look into what's causing that fever. That's what it says. Does a fever mean the patient is dehydrated and needs fluids? You absolutely can have fevers associated with dehydration if it is severe enough, because you cannot maintain homeostasis. Homeostasis is where we're maintaining our temperature. So you might have a fever, you might have an elevated temperature, especially if you are dehydrated after you run a marathon. But you also can have a lower temperature because of it, depending on what is causing the dehydration and what the person has been doing. But it's not specifically that, right? Okay. It guarantees that a patient has a bacterial infection rather than a viral one. BS all day long. No. Are you more likely to have a fever with a bacterial infection? Yes. Do viral infections ever have fevers? Have you ever had the flu or COVID? Okay. Next. What is happening? Did this freeze? No. Okay. It's just not going. Why is it not going to my next slide? Oh my God. Okay. We'll just click on it then. Cool. All right. Chapter 16, we have the complement activation pathways. Remember, we have classical, lectin, and alternative. And a little mnemonic here was antibodies like MAPS. And antibodies dealing with the classical pathway, like being lectin, and MAPS is, I guess, talking about, I don't even know why it's MAPS specifically, but I would assume it would be alternative, but maybe I'm wrong about this. Let's see what I wrote. Antibodies, dealing with antibodies and antigens, like being lectins, it's the lectin pathway. They are molecules that bind to mannose or other sugars on the surface of molecules. Sorry, I was looking at the MAPS thing because that didn't make sense to me at first, but MAPS is supposed to help you remember the alternative pathway. I guess because if you had a map, you could choose alternative pathways to go on a road. Cool. Antibodies like maps, y'all. All right, which of the following correctly describes the initiation of the lectin pathway of a complement activation? So lectin pathway is dealing with a molecule in your own body called lectin that can recognize sugars on the surface of microbes. These sugars often are going to be mannose, but remember, any sugar is going to end in ose. So if you see a ose out there, even if it's ribose or deoxyribose, those are sugars. Ose, sugar. Okay. So lectin pathway, we're looking for a sugar related thing here. A, pathways initiated by binding of antibodies to antigens. No, that's not antibody activated. It's sugar recognition. Pathways triggered by LPS, which is lipopolysaccharide, which is endotoxin. That's the alternative pathway. C, pathway begins when mannose binding lectin. Okay, lectin, here we go. And it's going to bind mannose. That's what we just said. Binds to carbohydrates on pathogen surfaces. Yes, this is exactly what we just said. Pathway starts when the complement complex binds to a pathogen surface directly, but we don't need any antibody binding. So just some rando complement binding to the surface of anything, that doesn't sound like that's safe. All right, in a clinical scenario, a patient with a recurrent infection with recurrent infections is found to have deficiency in C1q, which is a component of the complement system that reacts to the presence of antibody in the bloodstream. So right here, we could say, okay, it says C1q. That's not something you need to know off the top of your head, but it is telling us that we are not only talking about complement, which is how we abbreviate complement, C with the apostrophe. So it's complement, but it's also specifically the classical pathway because it's dealing with antibody. All right, so which complement pathway is primarily affected by this deficiency? Like we just said, that's going to be C. Remember, lectin is the lectin molecule that binds the mannose or other sugars, and the alternative is going to bind patterns like LPS. Okay. All right, next, complement cascade and the steps involved. First, it is initiated. It's initiated by one of the three pathways. Next, we have amplification. One molecule might get activated to start with, but it can activate a number, and each one of those numbers can activate several numbers, and so on and so forth. Sort of like when we think about amplification involved in PCR, it's like if you had one, then you go to two, two becomes four, four becomes eight. That's a cascade. That's an amplification cascade. Here, we're talking about turning a protein, changing it. It causes changes in these proteins. Those proteins cause changes in these proteins, and each one of them can be doing multiple. So that's amplification. Polymerization is whenever we're taking products from that whole setup, that whole amplification cascade, taking those products and putting them together to create a new molecule. In this case, we're bringing them together to create a pore in the surface of pathogens so that we can lyse them or cause them to break open. That's the membrane attack complex, and that's kind of the whole point of the complement cascade and what it's really bringing to the table. So into another party mess was my acronym. I had to work on this one to make it kind of work for me. But into is initiation, another is amplification, polymerization is party, and membrane attack is mess, because we're going to create a real mess for these microbes once our complement messes them up. Which step in the complement cascade involves the assembly of activated complement protein molecules to form a structure that creates pores in the pathogen's membrane? That's going to be dealing with the polymerization step, right? We're going to bring all those parts together to create that complex. A patient is diagnosed with a condition that impairs the formation of the attack complex, that pore forming thing. This person can't make the pores. Which condition would most directly affect, this condition would affect which step of complement cascade? Is it the initiation? No, we can still initiate and we can still amplify, but we won't be able to polymerize our complex. We can't build the complex. Does it have anything to do with clearing immune complexes? This is a whole other thing that we'll learn more about in chapter 17. Immune complexes are just when your antibody binds with antigen and you have buildup of antibody antigen complexes. And then your body needs to be able to clear those. And it's usually your macrophages that are going to eat those up and get rid of them, just like they would anything else. That has nothing to do with the complement. All right. For chapter 16, people have issues with MHC1 versus MHC2. MHC1 is found on all nucleated cells, and it presents antigen associated with stuff found inside of those cells. It's going to be recognized by CD8 positive T cells only. And the CD8 molecule on those cytotoxic T cells is what interacts with this MHC1 molecule. They have to interact while our T cell is recognizing the antigen on the actual MHC1 with its T cell receptor. So like this, I'll draw it for you, okay? If this is your T cell, and this is our cytotoxic T cell, okay? And this is its little receptor, and it recognizes this antigen that is being presented on the MHC1 on your infected cell. All right, and then this will be your CD8 molecule. So that's what we call them, CD8 positive T cells, because they are positive for this marker. CD8 interacts with MHC1 while the T cell receptor recognizes the antigen on the MHC1 molecule that infected cell is using to present the antigen. There are not specific MHC1 molecules for every antigen. MHC1 molecules can present any antigen ever. If it is in use in you and you think this might be alien, I will put it on my MHC, general MHC. Whereas the T cell receptor has to recognize that molecule that you said might be alien, putting it on my MHC1, T cell receptor has to see, I know this very exact part of this alien. So I'm going to, interact with my CD8 molecule. Oh yeah, you're presenting this on your MHC1. You're telling me this came from inside of you. I only deal with things that come from inside of cells. Now I kill you with granzymes and perforins. That's what's happening in our CD8 positive T cell response. That's an MHC1 driven interaction. MHC2, however, is found only on our APC. And what happens is we have a macrophage. So this is our macrophage. We'll put this, and this is our abbreviation for macrophage, okay? Anytime you see this means phage. So I sometimes use this with our bacteriophages. But M phage is macrophage. So whatever, he ate some stuff that is like these triangles that are out here, okay? And he ate one up inside of himself and then moves it because he found it outside and puts it onto his or hers, of course. It's MHC2. And that's going to be like this. Oh, this doesn't do that. Dang it. Whatever. Let's give her, sorry, let me do this right, because I know that this is something that helps people understand what's happening. Okay. So here's our antigen that we picked up from outside that we've put on our MHC2. It's really out of scale, but you know what I'm saying. And it's going to be recognized by the T cell receptor. Of a T helper. Okay, and this is a T cell receptor. Remember, MHC2, just like MHC1, it'll just pick up any antigen and put it up there and be like, does this look bad to anybody? And then our T cell receptor recognizes that specific piece of that alien that you found outside of the cell now. And it recognizes that and says, oh my gosh, I know this. This is what I was made for. I've been looking for this specific piece my whole life. And you are presenting it on, I can tell that you were presenting it on MHC2. And I noticed that with my CD4 molecule. So that's why TH cells, our T helper cells, are CD4 positive. And the cytotoxic T cells are CD8 positive. CD8 interacts with MHC1. CD4 interacts with MHC2. MHC2 presents stuff from outside. Outside stuff can only be presented on MHC2, which is only found on our antigen-presenting cells, our macrophages, dendritic cells, and our B cells. They are antigen-presenting cells. Anything can put MHC1. T helper cells do not interact with MHC1. They only have CD4. So only cytotoxic T cells are going to interact with MHC1 presented antigen. So their CD8 can recognize it. Then that triggers them to make their granzymes and perforins to kill that target cell. T helper cells, they need MHC2. Okay. That's how this is going to work. In public classes, help every time. What? So in here we're talking about the I in class 1. Public essentially is talking about, I guess, presenting endogenous antigens. Wow, this is just some letters. I don't know where. I guess the public is supposed to be telling you that it's endogenous, carried by professional antigens. I don't know. When I wrote this, it made sense. I swear to God it did. But now I look at this and I'm just like, this doesn't make a whole lot of sense to me. I don't know. Helpers. What is the every time thing? Maybe that don't make sense. Every focus on actuation of helper T cells. Time reminds that only specific cells are involved in expressing. That doesn't make sense to me. It made sense when I wrote it. Now it doesn't make sense. To me, the best way to remember it is just simply because of MHC1 looking like inside, and MHC2 doesn't look like inside. So that's how I remember it. MHC1 looks like I for inside. And this is all going to be inside related. So if something's inside of you, you want to kill the cells that have something inside of you. That's going to require killer cells, which are T cells, and CD8 versus CD4, right? So CD4 looks more like an H than an 8 does, and H being, basically T helper cells. T helper cells have the CD4. And if they're helper cells and they're not killing cells, then we aren't going to be interacting with the directly infected inside cells also. So that's another way that we can look at those being related to one another. So inside, that must be CD8, and outside. So that's MHC2. So it takes a little bit of roundabout thinking that way, but that's literally how I always remember it. I wanted that mnemonic to make sense, and it did when I wrote it, and now it doesn't make any sense to me when I read it on the second go around, and I apologize for that. Maybe you can make more sense of it when you read it. I don't know. Which type of MHC molecule is primarily responsible for presenting antigens from intracellular pathogens to CD8? We just said CD8 positive T cells, that actual CD8 molecule interacts with MHC1. So this is intracellular. So this is inside of the cell. Automatically, that should have you thinking MHC1. A patient with a genetic defect that affects the expression of MHC2 molecules would likely have difficulties with which of the following. So we know MHC1 is inside, then MHC2 is going to be stuff from outside. And that's going to be our T helper cell response. All right, are they going to have issues presenting endogenous antigens, so stuff from inside, to the cytotoxic T cells? No, that's MHC1. Are they going to have problems activating T helper cells and orchestrating the immune response? Yeah. Yes, they are, because you have to have that interaction in order to activate your T helper cells. And remember, these are our captains. All right, targeting cells infected with virus. That's going to be an internal thing, and eliminating cancerous cells, also internal. Okay, for the antibodies, what we need to know about is the class switching. So that is talking about switching from IgM to IgE, A, G, those guys. Okay, so switching there. And then also talking about activating B cells, switching to memory versus regulatory versus effector, which are our plasma cells. Clonal expansion is picking that one clone that has to do with whatever antigen you're looking at and not activating the other ones. And that your FC, your constant region, is the portion of that antibody that has to deal with what type of antibody we're talking about. So here our little mnemonic is a big cat switched gears. And that means activation of B cells. Cat is class switching. And then gears, I guess it's just talking about the different classes that you could be. Cat switching gears, class switching to the different classes. Cool. And then, of course, these were our different antibody classes that we needed to know. The IgM being, God, they stepped on that toy again every time. IgM is that first one that's made. It has minor functions. It's just not as effective as IgG, which is our heavy hitter, better long-term protection. It is the most abundant. It just does the most stuff. IgA is your mucosa secretory antibody. And then the IgE is allergies and parasitic infections. Yes, okay, we'll just move on. During antibody class switching, what change occurs in the antibody molecule? When you're switching classes, the thing that's different is your FC, or your constant region, right? Not your variable region. Your variable region is where the antigen interaction is happening. That was the whole point of activating that B cell, is because it interacted with that antigen. We're not changing that. We're not changing the specificity. So your constant region, the light chain is just that little piece that's off at the sides. When we draw it like this little piece here and this little piece, those are the light chains. That is not what we're talking about here. We're talking about the long pieces down here. This is the constant. The antibody switches from a monomer to a pentamer. No, that's not what the important thing is about class switching. And anyways, you start out as a pentamer and then become monomers typically, but you can be dimers. So patients diagnosed with an immunodeficiency that affects their ability to switch from IgM to IgG. Which of the following would be likely be true about this patient's immune response? IgM is not as effective as IgG, right? So what would the patient have normal IgG levels but low IgM? No, because they are fine with their IgM. They just can't make IgG. So you always start with IgM and later switch to IgG. So it's not this one. The patient would have difficulty producing effective long-term immune responses. That is part of what IgG's role is. So it might be this one. The patient would have high levels of IgE. This has nothing to do with IgG switching. And the patient would have an overproduction of IgA. Again, we're talking about IgM and IgG. Where are IgE and A coming in with all this? They're not. So it's going to be this one because IgG is involved in your long-term immunity. For the T helper cells and the regulatory cells that are associated with them, remember that you're always going to be starting out as a T helper, generally speaking. Then you're going to be activated. And you're going to become TH1, TH2, regulatory, and memory. So all of those. And that these two here, they're two separate things, but they are effector types. They're the ones doing the work. And we talked about how TH1 stimulates eventually our T cytotoxic pathway. And then these are going to stimulate typically our B cell pathway. And that's really what's going on here. And there's cytokines that you don't need to know. It's on here just to help explain the whole process that these things are going to deal with. This is 3 parents regulate home. So, I mean, we're really focusing here on the helper cells, the 2 helper cells, TH1 and TH2, and then the regulatory cells. There are also memory ones here. There's always going to be memory. Which helper T cell subset is primarily involved in promoting antibody production by B cells and regulating allergic reactions, which are governed by B cell antibodies? This is going to be these. A patient with an autoimmune disease has elevated levels of pro-inflammatory cytokines and increased levels of inflammatory response and reduced function of T regulatory cells. So we're not going to be regulating our response very well. So you are going to be more likely, of course, to have an autoimmune disease. So which of the following is most likely affected in this patient? Their ability to activate macrophages and cytotoxic T cells, the regulation of immune responses to prevent autoimmune damage. Okay, you're just giving it away now. The promotion of B cell antibody production and allergic responses, or the suppression of inflammatory response by eosinophils, which are innate cells. They have nothing to do with what we're talking about here. The top one, the only reason it gave me pause, the ability to activate macrophages and cytotoxic T cells. There are regulatory effects in place for that TH1 response, which is what is affected in A. That could be affected by your inability to regulate as well. But obviously here, we're more concerned about that part of it being the immune response. But again, it's not going to be that complicated for you guys on your test. Oh my gosh, there's more. Okay, so for the cytotoxic T cells, remember these guys are going to be activated by the TH1 response. They have to see antigen presented by MHC1. So we have T helper 1 cells giving them the go ahead. We have to see things that are MHC1 related. So antigen presented on that. And this means that our antigen came from inside the cell. And then we can make perforins and granzymes in order to deal with that. Real action kills everything is our mnemonic here. So which of the following molecules is released by cytotoxic T cells to induce apoptosis in infected or abnormal cells? Your CD8 positive cytotoxic T cells are going to be producing perforins and granzymes that are eventually going to lead to apoptosis of our cells. Apoptosis is the cell unaliving itself once it reaches a certain amount of destructed aspects. So a patient is experiencing a viral infection. Okay, cool. So we know we have an infection inside. And is found to have a deficiency in cytotoxic T cell function. So they don't have very good CD8 positive T cell function. What of the following is most likely to be directly affected by this deficiency? Okay, so is it the activation of helper T cells? That part happens before. You can't activate a cytotoxic T cell without having the helper T cell first. So that's not it. The production of memory B cells has nothing to do with your cytotoxic T cell response. Phagocytosis of extracellular bacteria by macrophages has nothing to do with your cytotoxic T cell response. The ability to kill cells infected with intracellular pathogens is exactly what your cytotoxic T cells do. That's where the problem's going to be. Please. Okay. So that is it for that part. I know it was long and I know it was a lot. These chapters are a lot. These two chapters 15 and 16 together, they go together, but it's a lot. So that is that part of it. So if you want to stay, I know it's already 11:44. I hear you, spaghetti. Anyways, God. Okay, so these are what I posted. Oh my God. Okay, fine. Why are you crying, buddy? Crying, you ball. Come here. Don't be fighting in here, though. That's the first thing they do. They immediately start fighting. Okay, so this is, guys, meatball, stop. This is the slides or whatever, the study sheets that I made for you guys that I was talking about in this post and at the beginning of me getting into all this. Hi, Ripley. I got 3 of them. That I put it together last night. So I reorganized it and then changed the colors so that I had sections that was easier for you guys to see. You guys didn't see it before, so I don't know why I'm telling you about me changing the colors and everything. It's not like you know how disorganized it was. But this is exactly what I'm talking about when you guys are making your notes. In order to make them useful for you, you might make random notes. Then it's a great idea to go back and reorganize them in a way that's easier for you to see, easier for you to read it, has the information that you need in order to make sense of it. So making notes is one thing. And then what I did was when I was making all of these, I went through the slides. And while I was going through the slides, also went through the study sheet. I know I say it, I'm going to say it one more friggin' time. I'm going to go through the slides and then I'm going to go through. Oh my God, meatball, what are you doing? Stop it. I'm gonna go through the slides and go through the study sheet at the same time and make sure that I'm getting all my information down, because I might be writing stuff down from the slides, and I sometimes do, that I will miss something on the study sheet. And guess what? That's okay. As long as you go back to it and realize, oh, I didn't write anything about, the complement cascade. And then you go back in and edit it into your notes. I had to do that with my chapter 15 because I left out a couple of things that I just didn't think about. And I wanted to add it in for you guys. It's not stuff that I needed. I don't need anybody to tell me that all the blood cells originate in the bone marrow, but maybe you do. I don't have any idea what you think you need, but it's in the study sheet. So I go in back and I added that in. So things like that. So I try to make sure I have everything from the study sheet in here with explanations that I thought were adequate for, explaining each of those topics. Does this have the exact same information as the study sheet? Absolutely. Is it written in a way that makes more sense to me when I read it? Yes. Is it organized in a way that makes more sense to me when I look at it? Yes. Will my sheet translate to make more sense to you than the study sheet and looking at that outline? How you look at that? Yeah, probably, because I've gone through and organized this. Can you make a sheet better than this one? I bet you can. And I dare you to. Okay. So you can use this as a template if you want to. You can even use the same freaking information. Please reword it in words that make more sense to you. If there's anything on my study sheets that you don't understand, you better be writing more about it on your own study sheet. Okay. Use it, but don't only rely on this, because if I wrote something that makes sense to you and you look at this and you go and take the test and you are like, oh, well, the study sheet said only these things. It didn't explain blah, blah, blah. Well, guess what? Whose fault is that? This is my study sheet. Okay, I'm gonna make it clear. This is my study sheet that I made, that I would make if I were taking notes on this class, having taken it, what I think I would have written down when I was taking it for the first time. Okay, so this is chapter 15. Obviously, I wrote that in the middle and has what I think is all of the chapter 15 information on it. And then chapter 16, it looks a little bit busier, but once you finally get down to looking at the boxes and what is where, it's not actually busier. To me, this actually, once you look at it and understand what's happening, is cleaner than the other one. I prefer this study sheet over chapter 15's because this one makes more sense to me. And I will kind of show you a little bit why. I don't want to get too much into drawing too much on it because it's so pretty and I just don't want to ruin it. But here, I'm gonna show you a little bit. So let me pick a random color that's not on here really. What color shall I go with? Let's pick a kind of darker. I don't know, this, whatever this is, ugly. This ugly color. Okay. So obviously up here in this upper left corner, I have reiterated that the bone marrow is where we get our B cells and T cells from, and that the T cells are going to be maturing in the thymus. Great. So that's where I started that. Then I have mention of our lymphocytes, all lymphocytes that we have, our LCs that I abbreviate so I didn't have to keep writing it out. Our lymphocytes are going to go through something called, and it says it over here on the far side over here, clonal selection. In clonal selection, we start out with all of the possible lymphocytes you can make. They go through clonal deletion. Those lymphocytes that don't react to self, right? Okay, those are the ones that are going to be left. Let me get rid of this before I forget to get rid of it. So those are the ones that are left. When they see antigen, only the one that recognizes that one single antigen is going to proliferate. Then after it proliferates, it's going to differentiate. It will be either memory, regulatory, or effector. And then our memory cells, that will include our B cells, our CD4 positive memory, or our CD8 positive memory. Or you can have regulators that are B cells, CD4 positive T cell regulators, or CD8 positive T cell regulators. Yeah, they all have that. Or your effector cells. Your effector cells for your B cells are called plasma cells, right? So this is where we are in case you're not following. But plasma cells make antibody. And here, if you follow these up, are the different functions of antibody. Okay, we'll come back to that. Our effector CD4 positive or helper T cells are our Th1 and our Th2. And our CD8 positive T cells are our cytotoxic T cells. So let's step back to our antibody producing B cells, our plasma cells, okay? Let's get rid of the ugly vomit color. Okay, so we'll start up on the upper left with our antibody classes, our IgM, IgD, Ig, G, IgA, IgE, whatever. And I have our brief explanations of what they do. So IgM being the first ones, and etc. We just went through this. I'm not going to say it again. Then over here, we have our antibody functions, our neutralization, coating, agglutination, antitoxin, complement, and opsonization. While I was writing these out, I'm trying to save space here so I can try to fit everything in one little thing. All of what I'm writing here, block binding, cover, clump, bind block toxins, classical, help phagocyte. These things make sense to me in terms of what I've written for the terms, for the functions. If it doesn't make sense to you, write more, okay? Please. Then we have the titer, which is out to the side out here. It's showing us that it's measuring serum antibody concentration. That's what those brackets are. You can write out serum antibody concentration if you want to, but that's what I wrote to make sense of it, okay? Then I have our little diagram of an antibody with our variable region that binds the antigen and the constant region that determines the function. And then the fact that they're called FAB and FC. Cool. Great. So we did the antibody stuff. Next, we have the CD4 and CD8 positive T cells. I've mentioned in CD4 positive that we have Th1 and Th2. Th1 is going to help stimulate our CD8 positive T cell response. Th2 is involved in stimulating our B cell response. CD8 positive T cells are our cytotoxic T cells. They produce the perforins and the gramzymes. The perforins poke holes and the gramzymes digest the insides, and that causes apoptosis, which is when the cell is going to kill itself. Okay, great. So now down in this bottom, I'm going to get to this whole bottom, like this left bottom area in a minute. But let's for now focus on the stuff that's down here, which is with the end of the chapter stuff. But that is talking about the primary versus the secondary response. That the primary has that latent phase because we're trying to activate everything. And the secondary is faster because we can make IgG right from the get-go from our memory. And that's our best antibody we have in our arsenal. Adjuvants are added to vaccines to improve our responses. And here's our little descriptor terms for different kinds of vaccines and how they are delivered. If you need more explanation on those words, you are welcome to add your own on your own slides. Okay. Then my bottom left. This is my walkthrough of what happens in an infectious response. Now I have this one written out here, and I am going to try to redraw it on a separate slide so that we can just see it as I talk through it all. But hopefully this will make some sense to you looking at it up front. Okay. I want to approach it. Yes. Okay. So we can always come back up here if we need to. I can point at the one that's already written here because I want to be sure that it is kind of online with that same one, because I know that if you guys are looking at this whole thing, you're going to want that bottom left area to make sense to you. So I want to have it kind of similar to what we already have going on. All right. So we're going to start off. Oh yeah. And I also have a little note up here in the, where the little virus picture is, where it says autism isn't caused by mercury in vaccines. I just had to shove that somewhere so that I had that on there because I didn't want to leave it out. All right, so we have a viral infection going on, okay? We have a viral infection. Here's our virus. And on our virus, we're going to have all these little spikes. Virus gets into your body and you're very first infected. It's not in a cell, right? It's just chilling outside of the cell. And in fact, every time that it exits a cell to go to another cell, it's usually spreading outside of cells, right? So at some point, viruses are outside, but at other points, they'll be inside. Viruses are a great way to look at our reaction that's going on here because they're going to have both outside and inside response, okay? So here is our virus. When we look at our virus, we can even, let me get a different color. We can even take this whole piece right here as the spike, which is how viruses get into cells, right? This is their key that they use on the lock on the surface of your cells. So here's your spike protein, and this is going to be representative of our antigen, which we abbreviate as AG. Great. And we can also even look at the little end of this, specifically this part here. This is part of the spike. And that'll be our epitope. That's the part that our lymphocytes are going to recognize. Okay, so that's just setting the stage for all of this. First things first. I am a neutrophil, and I'm going to come along, and of course this is not to scale. And maybe I recognize something about this virus. Let's say it has double-stranded RNA in here. So that's the PAMP. And this guy has a receptor on the surface that recognizes that PAMP. This is just an example, right? So this is our neutrophil. Some mast cell or somebody in the area came along and realized something was wrong in the area and started sending signals. But this is where we're starting, is where our neutrophil, our innate phagocyte, right? It's going to phagocytose, it's going to bind to that PAMP and recognize it, and then phagocytose and eat up this guy. So he's got granules in him because he's a granulocyte, right? That's what that is. So this stuff lets us make signals. It lets us eat up these guys and whatever. So we're going to ingest him into our phagosome and break him down. So then this whole mess becomes the neutrophil that ate up the virus. Into a phagosome. Why are you crying? And there's just granules and stuff that's going to break down this virus and whatever. What is that noise out there? And then that is going to become the neutrophil pooping out the virus particles. Okay. So now we've got virus particles out here. Great. It doesn't do anything helpful on its own, right? But now let's say this is in your lymph. Well, it's in the area wherever we digested this out. But with the fluid that all of this was in, hanging out in, this is going to be in your fluid that's entering your lymphatic system. And that is going to bring it into a lymph node. And inside of this lymph node, I'm going to put a nice happy little B cell. And on the surface of this B cell, that will freak me out, we have IgD, or our receptor. And one of these guys comes up and interacts here. Okay. What's going to happen next is this whole thing. Nope, that's not what I wanted. This whole thing. A hawk. This is going to become then a B cell because it recognized it with its receptor. That is then going to be presenting that on This is massive, but I need the space to write in it. MHC2. Okay. Dun, 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 dun. There we go. Okay. So it does this. And then we have our T cell. Dun, 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 dun. Let's give him, can be blue. Let me make him a lighter blue so I can see it better. Okay. So then we have our T cell. This will be our captain. And he's just hanging out. He could be in the lymph, maybe. He's in the bloodstream. It doesn't really matter. So he's coming through the lymph node, let's say. Okay. And all this is going on in the lymph node. It's fine. It doesn't really matter. But he has a T cell receptor. And then this, okay, let me put him like this, T helper. He's just T helper. He's not TH1. He's not TH2. He's not TH regulatory. He's not, no. Okay. And neither is the B. They ain't done that yet. We're not there yet. Okay. So this guy, he on his surface has, if you guys will remember, sound effects for him. This is CD4 because it recognizes NHC2. So now this guy can send signals to that guy. And this guy can send signals to this guy. Okay. And then this goes a couple different ways. Okay. So the B cells can go do, let's do, yeah, okay, we'll do memory. These are memory B cells. These are regulatory B cells. And then we will have plasma cells. Stop that. Oh. Plasma cells are going to make antibody. And that's going to start out as IgM, which is eventually going to make its way to become IgG and others, okay? So we'll put plus, that's fine. And have their nice little functions. I'm not going to talk about the functions here because that you can look up here. Okay, great. So now we're at our T cells and we are at we are going to have also memory and regulatory. But these guys are going to also have so now we're finally getting into this whole idea. And so remember that whenever we're talking about this is our effector for the plasma cells, and these are our effectors sorry. Effectors for these guys, okay? Really bad handwriting. Actually, let me rewrite it because it's really just that bad. Stop. Okay. Okay, so our TH2 response is going to be involved in helping with more of our B cell response. We started off right off the bat activating our first B cell there, but we can help continue with our IgM to IgG stuff, help activating even more B cells and doing more of that side of things with our TH2 response, all right? Our TH1 response, however, is going to be a different thing. Here, we are going to get a whole other color, and it's going to be green this time. And in our green, we are going to have our cytotoxic T cell. And they are out during this whole infection, they are out interacting with cells that are infected. And they got all this crap from the virus in them. And on their surface, they have, actually, let me do this. Give me just a sec. So I want to draw my MHC thing bigger. Okay. Because the other one had to be big, so does this one. Is that big enough? I don't think it is. So this is MHC1. And on its little surface, we have this. And on our T cell surface, move this guy. Whatever, that's our T cell receptor. And we also have CD8. Now, this is nothing until you get signals also at the same time from an activated, previously activated, already activated, right? Because he's already TH1. He is going to come send signals in with this whole process saying, I approve that you guys are interacting. After that, actually, let me back this up a little bit. Let's do this. I wanted this smaller. once we get that signal, then we can make our, this is going to be granzymes and perforins. All right. Am I missing anything? Does anybody see anything that I am not explaining that you guys would like me to go into more detail with this? This has a little bit more explanation on this picture up here, but hopefully now this one makes a little bit more sense to you guys. I should have used probably the same colors. That's my apologies. But I used orangey color for the cytotoxic T cells up here at the top. I took a little more time on this one because I knew that this was probably the slide that everybody was going to keep around, but I figured talking through it actively might be also another thing that would be useful. So keep in mind here that when we have this first initial activity going on here between this B cell and then interacting with the naive T helper cell, B cell in this case is our antigen presenting cell. Remember, our antigen presenting cells can be B cells, macrophages, or dendritic cells. So up here, when I drew it, and I will use the ugly highlighter color, but up here, whenever I drew it, I have our macrophage down here. That is our antigen presenting cell. The end result is not any different though, okay? Here, when we have activated our macrophage, right, we see that down there in that ugly color, we picked up some crap, interacted with our T helper cell there. It differentiated into these different kinds up here. All right, you follow Th2, it activates the B cells that will also have picked up stuff from the lymph nodes in the same fashion that we showed down there. It's just we already have an activated Th2. We're not simultaneously activating, right? It's just already been activated. And now we can activate our B cell, become memory, regulatory, and plasma to drop the bombs of our antibodies. Our Th1 cells, however, are going to be the ones that will be activating our cytotoxic T cell response. We can't go kill infected cells that are waving the red flag, help me get the alien. We can't do that until we have our cytotoxic T cells activated by signals from our Th1, in addition to also having MHC1 presenting the antigen from the infected cell and our CD8 molecule on the outside of our cytotoxic T cell interacting with that MHC1. So that's the idea of what's happening in a typical infection. If you guys ever want me to break this down as far as how we're rejecting tissues, then we can do that. I will wait for chapter 17 to do that, though. Chapter 16 is, we're just going to focus on the infection side of it. Okay. So having done all of that, yeah, okay. Do you guys have any other questions for me?
No, I don't. I just wanted to tell you that, on that Sunday thing we talked about sending notes, I tried to send them from my phone and my iPad, and I don't know why, but it would, every time I uploaded it, it said something went wrong on from both of my things. I just didn't want you to think I wasn't keeping my word and following through with that.
That's okay. We can always, if you want to come catch me on Tuesday after class or after lab, whatever, and we'll see if we can't figure out something that'll work better for you, or we can just like look over them really quick. I don't anticipate it'll take like super long or anything. So
Yeah, I was like, man, she's gonna think that I just don't care. But I literally was trying, and I was like, oh my God. So I just wanted to let you know it wasn't me not keeping my word. I was just I don't know why it wouldn't upload my photos. Then I tried to do like a recording, and I was like, try to send it that way, and it wouldn't work. So that's
yeah.
what.
No worries. Yeah, I don't worry. I'm not at all thinking that you're somebody that's not trying. You're the last person I would think, because you always let me know, okay, I've been working on this. How can I be doing that? Can we make an appointment to work on this? And you're trying. I would never think you were not trying. And yeah, if we can't get that to send, we can either try to find a way to either like zip it, like sometimes if we can like compress the file like as a zip file, it'll send, or we can find like maybe another format and we can look at that stuff, or I can just, look at your notes with you. So
Okay.
we'll figure something out though.
Okay, well, thanks. Sounds good. And thanks for today.
Yeah, and of course I'll post all of this once it's uploaded.
Okay,
All right.
appreciate
Thanks so much.
it. Bye.
Bye.